So our project will be done over Simson's theory. The theory was founded by Robert Simson, who was a professor of math at the University of Glasgow from 1711 until 1761. Something cool about him is that the Simpson line uh, was named for him, but he actually didn't discover it. Anyway, this project was done by me, Ray Shaw, Chow Lee, and Matthew Barnes.
Given triangle ABC, there is a unique circle through triangle's three vertex. This is called the circumcircle. Also, triangle ABC is inscribed in this exactly one circle.
We have a triangle, ACB, which also happens to be a isosceles triangle. So what Pon's Theorem is trying to prove is that angle CAB is equal to angle CBA because sides AC and AB and CB are congruent. So how it does that is an altitude is drawn. This altitude is CD. Since an altitude, it forms a 90-degree angle where it intersects with base AB. And in doing so, since we know that AC is equal to CB and CD is a common side, using the hypotenuse leg theorem, we can conclude that triangle ADC is equal to triangle BDC, and hence their respective angles must be the same, which would be angle CAB is congruent to angle CBA, and hence angle CBA is equal to angle CAB because BC is congruent to AC. If this triangle is not isosceles, then we can't really prove that these two angles are the same because in reality they would not be.
Given a line segment AB, assume that CD is the perpendicular bisector of AB in this figure. This means D is the middle point of AB, and CD is perpendicular to AB. The locus of all points equidistant from A and B is the perpendicular bisector of line AB, which means AC equals BC.
Per se. And so let's say we've got F in this case. F divides AC into AF and FC, which are equal, and it's a perpendicular bisector, so it forms a 90-degree angle. It has to intersect with another bisector, EO, which bisects BC into two equal halves, and the point at which this intersects, we know it must be equidistant from all 3 points because we know that FO is the locus for all the points between A and C. So everything A and C related must lie on there, and it's equidistant from both of them. And we know EO is the locus for all the points between B and C. So if we combine the two, the point O at which EO and FO meet must be equidistant from B and C, from EO, and must be from A and C, from FO. And hence, it must be equidistant from A, B, and C. And that's what makes it the circumcenter, because each radii should extend to each of the vertices, and it does in this case, and it's the same angle. The angle of, in this case, angle AOB is equal to the measure of the arc AB. And the reason for that is because with a central angle, it's equal to r times theta for the length of this arc S, or in this case, the arc is AB instead of the general form of S. However, instead of multiplying by the radius, we are assuming we're taking only the degree measure and not the true length of it, and hence angle AOB is the measure of the arc. Inscribed angles. Inscribed angles, they connect. They lie inside the circle, and they don't meet at the center. They meet at another point on the circle. So in this case, P lies on the circle O, and it forms an inscribed angle, angle BPA. We know that O is the center and AP is a diameter. So, looking at this, you know that angle AOB is a central angle, and so it must have the measure in degrees of this arc AB. Since AOP is a straight line, angle AOB has a supplement to it, which is angle BOP. However, we don't even need to show that. We know that this is an isosceles triangle because OP and OB are both radii, and so they must be equal. But anyway, we know that since AOP is a straight line, that angle AOB plus angle BOP is equal to 180 degrees, which is equal to the sum of angle OBP plus BPO plus POB. And from that, we can see that angle OPB plus angle OBP is equal to angle AOB. However, we know that angle OPB must be half of angle AOB because since the isosceles triangle by Pons' theorem, angle OPB must equal angle OBP. And so from there, we see that angle BPO is half the central angle, and hence it must be half of the subtended arc. We got a diameter BOC. We know it's a diameter because it was drawn by construction, and O is the center of the circle, and it's a straight line that passes the center of the circle, so it must be a diameter. But anyway, if you've got a diameter, and in this case BOC, and you've got another point which connects to both B and C, in that case we call that A. So angle BAC must be equal to 90 degrees because we know that it is an inscribed angle as it's looking at the opposite side or the opposite arc of this circle, and it is a point not located in the center but rather located on the opposing side of the circle. And so we know that since BOC is a diameter, it must cut the circle into two equal parts, which must equal 180 degrees, as we know that the complete arc length of a circle is 360 degrees, and if you divide that by 2, since it's the diameter, you get 180 degrees. So we know that since the inscribed angle must be equal to half the opposing arc, half of 180 degrees is 90 degrees, and hence, no matter where this point A is located, it's still going to be looking at the opposite side, and so it must be 90 degrees, which makes the triangle automatically a right triangle. We know that the pair of opposite angles must be supplementary to one another. How do we know that? Well, because looking at this figure, we've got angle ADC and angle ABC. Both of these are opposite to each other. And so to prove that we're supplementary, we know that angle ADC is a inscribed angle, and so is angle ABC. Angle ADC overlooks arc AC, whereas angle ABC overlooks arc ADC. When you add these two arcs, ADC plus ABC, you get the entire circle. And since the entire circle has a measure of 360 degrees, half of that, which would be equal to the sum of both the inscribed angles from the formula that we've discussed a lot in depth, we have that the sum of angle ABC and angle ADC must be 180 degrees, as that encompasses the entire circle. If the quadrilateral is not inscribed, then it's a different story, but in this situation it is, and so that is the story, is that they're supplementary, because supplementary means that the two angles must add up to 180 degrees, and they do in this case. Where three altitudes meet in the middle. The reason they meet is because of the ratios that they apply in this diagram, CQ over QA times AP over PB times BX over XC, that is going to equal 1. And that's why that they converge. It's just the beauty of those ratios. It all works out to equal 1. Because if all three of those ratios equal 1, then the points will converge, or the lines will converge at a single point. And they do for this case. So the orthocenter is just where the three altitudes meet, and we typically call that as H. That is what we will be referring to it as we did in this diagram, and probably in every future diagram that we have the orthocenter labeled as. The orthocenter of a triangle lies on the circumcenter if and only if the triangle has a right angle. In this diagram, we see that the right angle lies at vertex AH, making an angle CAB as the right angle. The reason it can only lie on the circumcenter if the triangle has a right angle is because this triangle is also an inscribed angle looking at arc BC, which we proved before is equal to 90 degrees, since we know that BOC is a diameter. And we also know that AH is the orthocenter because what we can see from this diagram that CH is an altitude as it forms a 90-degree angle with the base AHB, and we also know that that BAH is an altitude as it forms a 90-degree angle with base CAH, and it originates from vertex B. And so we know that since two of the altitudes converge at one point, that the third altitude will as well, and thus making AH the orthocenter. So, for the proof of this lemma, it states that if x and z happen to be the same point, then there is really nothing to prove. So we can assume that x and z are distinct, and our goal is to prove that xz is parallel to QA. If P is at the point B, then x and z are also at B, and since we are assuming that x and z are different, this does not happen. Thus, P and B are different, and we can consider the unique circle having diameter PB. Since angle PXB is equal to 90 degrees is equal to angle PZB, it follows that points x and z lie on this circle, and thus angle PXZ is equal to angle PBZ, since these angles subtend the same arc in that circle. But, assuming that P is different from Q, we see that angle PBZ is equal to angle PQA because these angles subtend the same arc in the original circle. Thus, angle PXZ is equal to angle PQA, and it follows that XZ and QA are parallel as designed.
And since Z and Y lie on two lines through the same point that are parallel to each other, Z, Y, and X must be collinear. Similar reasoning would hold if we were to choose an altitude dropped from point B or point C. That is, we know that when P does not lie on all the altitudes simultaneously, that X, Y, and Z are collinear. The only case left is when P lies on all those altitudes, that is, P lies on the orthocenter of ABC. But we also know from the theorem that P must lie on ABC's circumcircle, and from our previous section on the orthocenter's relation to the circumcircle, we know that that guarantees that triangle ABC is a right triangle. Then, taking, say, A as our right angle, as we did in that diagram, then we know that P, A, Z, and Y are all the same point. And since we only have to choose the line through Y and X then, which would necessarily go through Z, they are also all collinear. Therefore, for any point P on the circumcircle of ABC, we can show that points Z, Y, and X are collinear, thus concluding our proof of Simson's theorem itself.
Dr. Muhammad Akbar for being the best professor that we have ever had. Also, we'd like to thank our textbook, well, not thank, but reference our textbook, Geometry for College Students by I. Martin Isaacs, for providing us with the basis for our theorems and proofs, and giving us examples for diagrams. We'd also like to thank GeoGebra for allowing us to make the diagrams pretty easily. And also, lastly, this project was made by Matthew, Chow, and I for geometry, also known as Math 3321 at the University of Texas at Dallas in the spring of 2019. Anyway, thanks for watching.